All right, guys, before we get started with the lesson today, are there any questions over any of the assignments thus far? Any questions over any of the assignments thus far? .6, so we started yesterday. Guys, any questions over any of the assignments thus far? So where we're starting today is with this one here. We're going to skip the problem after the one we finished up with, and look at this one here. Now this is going to be the exact same as what we did before. We're finding the polynomial that has the zeros of -1 and 4i. -1 and 4i. And what that's telling us is that x is equal to -1 and x is equal to 4i. We will have these two solutions for sure. Yes, sir.
Where does it say the white letters?
I do not know.
I think I have a hunch that it said that for years.
Possibly. All right, guys. Now there's one other solution that this will have. Is it will have -1 and 4i, but the other solution would be? Guys. -4i, because if a plus bi is a solution, then a minus bi is a solution. Since 4i is a solution, -4i has to be a solution. We have to have their conjugates. If we have one, we have to have the other. Now at this point here, we're going to set each one of these equal to 0. So we're going to add 1 to both sides, telling us x plus 1 is equal to 0. Next one we're going to do is we're going to subtract 4i from both sides, telling us x minus 4i is equal to 0. And the last one here, we're going to add 4i to both sides. And when we add 4i to both sides, we get x plus 4i is equal to 0. Guys, let's put the Rubik's Cubes away. All right, guys. Once we get all three of these here equal to 0, we're going to multiply them together. So we're going to have x plus 1 times x minus 4i times x plus 4i equals 0. Okay, guys. So now at this point here, we need to multiply these together. And when we multiply them together, we're always going to multiply the complex conjugate or the conjugates together first. So we're going to be multiplying the x minus 4i and x plus 4i together first. Now when we multiply these here together, well, we'll do x times x, which is x squared. Then we'll do x times 4i is going to be plus 4xi. Then we'll do the same thing with -4i. So -4i times x is going to be -4xi. And lastly, -4i times 4i is going to be -16i squared is equal to 0. And when we look at this here, well, the middle two terms, 4xi and -4xi, those will cancel out and be 0. Now we said I squared is what? I squared is -1. Now, for the most part, as long as we don't get to powers bigger than 4, typing negative 16 I squared into the calculator, it'll tell us exactly what it is, which is going to be positive 16. Because I squared is negative 1, so really what we are saying here is negative 16 times negative 1. Well, the negative and negative make a positive. So what we're left with is our x squared plus 16. Questions on this here? Questions on any of this here so far? And last but not least, we need to distribute this through. So we're going to multiply through by x. So x times x squared is going to be x cubed. X times 16 is going to be plus 16x. Then we'll do the same thing with 1. 1 times x squared is going to be plus x squared. And lastly, 1 times 16 is going to be plus 16. Now looking this through and looking at all the terms, there are no like terms, but what we can do is rewrite it in standard form, which will tell us that we have x cubed plus x squared plus 16x plus 16 is equal to 0.
You excited for the ACT tomorrow?
Yeah. Give you all another chance to earn more scholarship money and take college classes earlier. You don't have to take 0 level courses if you get above a 19 on math and English.
What if I'm not going to college?
You're still going to need to take it. You're going to be able to go back if you want to and change your mind. You still have that score to help get you scholarships. And it also helps the school. It will help the school how well we're doing. Yep. But you're required to take it in the spring. But then how can you get better scores if you don't practice? The last thing we're covering in chapter 4 is Descartes' rule of signs. Descartes' rule of signs. Descartes' rule of signs. Now this here will tell us, using this theorem, we're going to be able to find out the number of possible positive zeros, negative zeros, and complex that a polynomial function can have. Guys, put those away. When we look at the Descartes rule of sign, the number of possible positive zeros we have is equal to the number of sign changes of the coefficient of f of x, or less than that by an even number, or less than it by 2. And we could keep subtracting 2 from it to know the number of possible positive zeros. To know the number of possible negative zeros, we take the number of sign changes of f of negative x, or it's less than it by an even number, or less than it by 2. Now this here, we're going to go on and look at it because it's going to be a little bit easier to see it when we actually work through one of the problems. So when we look at positive zeros, so we're just going to look at the normal function itself, x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x cubed minus 6x squared minus 8x minus 8. So we're going to look at this one here. We're looking at this function here. And we're going to count the number of sign changes from one term to the next. And that will tell us the number of possible positive zeros. So if we go from x to the 6th to the x to the 5th, does the sign change? Because x to the 6th is positive, x to the 5th is negative, so this would be our first sign change. Then we look from x to the 5th to x to the 4th. Does the sign change? So that would be our second sign change. Then we do the same thing from x to the 4th to x to the 3rd. Yes, because it goes from positive to negative. Now we look from the next one, x to the 3rd to x squared. Does the sign change? No, we go from negative to negative. From x squared to x is going from negative to negative, and lastly, from negative x to negative 8, no. So the number of sign changes that we have is 3. So the number of possible positive numbers that we can have is 3. Questions on this so far? Now we need to find the total possible negative. And for the negatives, we're replacing x with negative x. So every place where there's an x in this function, we're going to replace it with negative x. So every place where there's an x, we're going to replace it with negative x. And we're going to simplify this here. Now, one thing that will make this easier is we've seen already whenever we square a negative number, it becomes positive. Negative 2 squared. Negative 2 times negative 2 is positive 4. Whenever we put a negative number to an even power, the sign, that negative inside, becomes positive. Whenever we put a negative number to an odd power, it stays negative. So negative x to the 6, well, it will be x to the 6. But really what we have in front is negative 1 to the 6th power. And we could do that in a calculator and say negative 1 to the 6th power, and it's going to become positive 1. The sign's not going to change. But if we did it to an odd power, negative 1 to the 7th, it's going to be negative 1. An odd power is going to stay negative, and even power is going to become positive. So here, negative x to the 5th, well, we'll still have that negative. It's going to change the sign. So since it was negative 2, it's now going to become positive 2, and we have our x to the 5th. Because we're really saying negative 2 times negative 1, the negative and negative would make a positive. Our next one, well, we'll still have x to the 4th, but since that negative is applied to an even power, it's going to be positive, so the sign's going to stay the same, which is plus 3. The next one, negative x to the 3rd. Well, we'll have x to the 3rd, but a negative to an odd power is going to be negative, so the sign's going to change from negative to the next one, negative x squared. Well, it's going to be, and it's going to stay the same, so we'll have minus 6x squared. And we look at the next one. Well, the power for this here is 1, which is odd, or it's going to change. Here, since we don't really have an exponent, we can just say negative x times negative 8. Negative times a negative is a, so we have plus 8x minus 8. Questions on how we got to this here? And really that understanding that if the power is even, the sign stays the same. If the power is odd, the sign changes, will make this go a lot faster. Now we just need to count the sign changes. From x to the 6th to x to the 5th. It doesn't. We're going from positive to positive. From x to the 5th to x to the 4th. No, we're still going from positive to positive. From x to the 4th to x to the 3rd. No. X to the 3rd to x squared is our first one because we're going from positive to negative. From x squared to x is our second one because it's going from negative to positive. Put that away. And the last one from positive to negative. So the most negatives we can have is 3. So we can have 3 positives and we can have 3 negatives. Any questions on this so far? We have any questions on how we found the positive or negatives? Now, at the start of this here, I said we could find the positive, negatives, and complex, yes? For the theorem, we only had 2 main parts, didn't we, for positive and complex, or positive and negative? Well, we can do that, and what the answer for these here are going to be in a table, because we'll have positive, negative, complex. And we're going to set this up here. Now, I'm going to add 1 here for the first one, just so we can see it. For y'all's answer, you don't have to include this last one. But I'm going to include 1 that just says total. Because when we did this here, we counted up. We got 3 for positive, yes? And we got 3 for negatives. How many total solutions can we have for this polynomial? 6, because the degree is 6. So the total number of solutions I should have is 6, yes? C would be 0. Because if I have 3 positive, 3 negative, I have a total of 6. How many should I have? Do I have them all? Because if I have 3 positive, 3 negative, that gives me a total of 6. I should have 6. We have them all, so that means there should be 0 complex. Now, and it said on both of these here, we can have that number or less than it by an even amount. So the even amount I always pick is 2. And I start with the negatives. So I could have 3 negatives or 2 less than it. So if I subtract 2 from 3, I get 1. So we could have the case where we have 3 positives and 1 negative. But again, how many should we have total? If I have 3 positive and 1 negative, do I have 6 total? I only have 4, yes? How many are missing? So how many complex? So it could be that I have 3 positive, 1 negative, and complex, which still gives me a total of. Okay, can we reduce the number of negatives by 2 again? Well, 1 minus 2 is negative 1. We can't have that. So again, when I start doing this here, I always decrease the negatives by 2 until I can't anymore. Once I can't decrease these by 2, I put it back to the total number. Because the most we could have is 3, yes? But which one can I decrease by 2? The positives, yes? So I have, the first 2 are all the possible combinations I could have with positive values, 3 positive values. But if I subtract 2 from it, now we're going to look at all the cases where we have 1 positive. So I could have 1 positive, 3 negative, and complex to get a total of. Okay. Now, we can still decrease the number of negatives. Not scroll. By 2 to have 1. But we'll still have 1 positive, because we could have 1 positive, 1 negative, and we still need 6, yes? So we're missing how many? Complex zeros. Can we decrease the negatives any further? Can we decrease the positives any further? So, these here are all the different possible combinations we can have. And this is helpful, especially when we're solving, because if we're having trouble seeing the number of zeros, this is helpful, as we saw the other day with the rational zeros theorem, where we had 32 possible solutions. That's a decent amount. It could be higher. I've seen some that I did years past. I did one, I set it up for the pre-calculus class that ended up having 140 possible rational zeros. But this here tells me and limits the number I can have. Because if we graph it and we have 3 positive numbers, that means it's one of these two here. Either I'm going to have 3 positive and 3 negative, or 3 positive and 1 negative. If we graph this, and again, the x values only go between -10 and 10 on the standard axis. And we had this set up here. Well, this crosses 2 times on the positive and 2 on the negative, yes? Well, that means these bottom 3 aren't going to work. Because the top one, the very bottom says 1 and 1. The graph tells me I have 2 and 2, yes? So that means having 4 complex isn't going to work, because we already have too many. Having 2 complex is not going to work, because we have how many positive? 2. So the only case that actually does work is we have 3 positive and 3 negative. All that's telling me is that somewhere possibly out to either side, and this is just a random sketch, it's not the actual graph, to either side is another solution we just don't have. We'd have to go above and below -10 and 10 to find the third. It gives us an idea of what the other solutions will be. Does this make sense here? Yes? So if we take this, and especially some functions that are harder to solve, if we put this with the rational zeros and graphing, it takes the number of solutions that we could have and what we're looking for and narrows it down so we know what we're going to have. Questions on this here? We're going to skip that next one. I want to look at this one here. Yes. Yes. No. Get it on the way back. 1 says I want to look at this one here, and 2, this one's easier to read than the last one. Now with these here, you don't have to rewrite the function out for the positive case, because they already gave it to us. Because we're really checking the sign changes for the function we're starting with. So what we could do is just here, see where the sign changes. So from x to the 4th to x to the 3rd, does the sign change? Yeah, it goes from positive to negative. How about from x to the 3rd to x squared? Yes, because we go from negative to positive. How about from the square to x? And x to our number? So the number of possible positive numbers is 4, yes? Well, how many possible solutions can we have? 4, the degree is 4. So do we have all of them? Yeah. So really, what is most likely the number of negatives we'll have? 0, because we already have all 4. Now we can look at the negative case, guys, which is replacing each x with negative x. And the ones that have an even power, the signs are not going to change. The ones with an odd power, they are. So if we look at 3 times negative x to the 4th, we will have x to the 4th and 3, but since it's an even power, the sign will stay the same. Since it was positive, it's going to stay positive. Our next one, we'll still have our 7 and we'll have x to the 3rd, but since the power is odd, the sign's going to change. Since it was negative, it's now going to be positive. The next one, we have negative x squared. Well, the x is going to be squared, but since it's an even power, the sign will stay the same. The next one, the power is odd, but since it's really to the first power, we can multiply them together. Negative 13 times negative x, the negative and negative makes a. Plus, we have plus 8. And if we look at all these here, the sign does not change at all. It's all positives all the way across. Positive negatives complex. And this is, I won't do the total. When I do these here, I don't put the total one up, mainly because we know, looking at the degree, we can tell how many we should have. Now, the total number of possible positives was 4. And as we saw, the total possible negatives was, and the complex is 0. Now, if one of these does hit the maximum 4, then the other one's most likely going to be 0 for positive and negative. Will it always work out that they equal the total degree? Not always. There are some that I've seen where we don't have the total number, but it could work out that way. Well, looking at this here, we can't decrease the negatives by 2 because it's 0, but we can decrease the positives from 4 to 2, 0. The number of complex is going to be 2. And again, we can decrease the positives by 2 to 0. The number of negatives is still 0, but our number of complex is 4. We can't decrease the positive anymore, so this is it. Now, the number of number of complex for any of these tables here will always be an even number. It'll always be, well, you can't necessarily say even because 0 is not even, but we won't have an odd number there. So 1, 3, 5, 7, 9 will not be any numbers for the complex. As our complex conjugate theorem stated, if A plus BI is a solution, then A minus BI is a solution. They are always going to come in pairs. So if we have one complex solution, we have to have a second. And that is helpful because if you're working these here and you're adding them up and seeing what's different, and that list is an odd number, 1, 3, 5, 7, 9, then something went a little wrong. Go back and look. Now, for positive and negative, we can have odd numbers for those, not complex. Complex is going to be either 0 or a multiple of 2. Any questions on any of this here? And that is it.